possibility. The milkman, the paperboy, the evening TV. Everywhere you look, there's a heart, a hand to hold on to. Everywhere you look, there's a face of somebody who needs you.
Earth, quake, resistant buildings. The three techniques that we researched to build an earthquake-resistant building are base isolation and damping, cross-bracing, and shear walls.
The two main types of base isolation are sliding and elastomeric.
Sliding base isolators limit the strain on the structures across the isolation interface, and there are two different types of sliding base isolators.
They include spherical sliding bearings and friction pendulum bearings. Spherical sliding bearings are built with rubberish pads with a curve in it that allows the building to have full range of motion.
Friction pendulum bearings are constructed with an articulated slider, a spherical concave sliding surface, and an enclosing cylinder for restraint. All of these things help allow the building to have complete flexibility during serious shaking of the earth.
The next form of base isolation we researched was elastomeric bearings.
Elastomeric bearings support vertical loads with little compression. The elastomers, or the rubberish part, allow for expansion and contraction of the base. In between layers of elastomers are steel plates called shims.
This design allows for vertical stiffness that holds the weight of the building. It also allows for horizontal flexibility that converts detrimental vibrations into gentle shaking.
A south lead plug is often put in the center of this bearing for damping. Damping is a decrease in the amplitude of vibration.
The three types of damping we researched are supplemental, fluid, and friction dampers. Supplemental dampers can either be combined with base isolation or higher up in the building in the cross braces. They can be added to pre-existing buildings as well as constructed with them. This type of dampening device is mostly used in tall buildings that can't be properly base isolated due to their tremendous flexibility. This leads to the necessity to control the horizontal displacement. Fluid dampers are shock absorbers that contain stainless steel pistons and fluids such as silicone oil. The special passages created by the pistons alter the flow of the liquid, thus altering the resistance characteristics. Friction dampers use metal to absorb energy through friction. Steel plates slide against each other in different directions and are separated by shims. They are used in cross braces.
Another technique in constructing earthquake-resistant buildings is cross-bracing. Cross-bracing is a system used to reinforce building structures with diagonal supports, which can increase a building's capability to withstand seismic activity. The cross braces should be oriented as seen here. They are designed this way to distribute the weight of the framework of the building evenly.
In normal buildings, the framework is just a hollow space. If an earthquake were to occur, the walls would collapse. With the addition of cross braces, the walls are supported. Metal is a sturdy material used to construct cross braces, and when attached to large scaffolds, the wall is very strong. Scaffolds are large frame structures, such as ones used to raise window washers.
Cross-bracing is a great method for disaster-proofing buildings. However, it will only work if the foundation is solid enough. The last technique that we researched in earthquake-resistant buildings is the use of shear walls. Shear walls are additions to a regular wall composed of brace panels, also known as shear panels, to minimize the damage of the lateral shaking that seismic waves produce.
Typically, shear walls have four components. These include wood framing, sheathing, nails, and hold downs. The length of each wall is determined by the location of the hold downs. After researching different techniques to build an earthquake-resistant building, we decided that it was important that our building was constructed with cross braces and a base isolator.
In our initial sketches, we wanted to compile all of our research into one building.
Each technique we researched had multiple variations, so in our sketches, we wanted to explore different possibilities.
In my first sketch, I tried the inverted V cross braces with elastomeric base isolators. Our research supports this idea. We found that elastomeric bearings are commonly used in base isolation because their composition of an elastomer and a shim.
In my first sketch, I used the X cross braces, shear walls, and elastomeric base isolators as well. Through further discussion, we decided the use of shear walls would be very difficult to build in model size, yet highly recommended for real buildings in seismic zones. We also decided against X braces because we wanted to save our wood to use in other structures throughout the building.
My second sketch is very similar to my first one. The only difference would be using wheeled isolators instead of an elastomeric one. I thought this would be beneficial to the building because the entire building, including the foundation, would be able to move laterally.
My second sketch included inverted V cross braces and a sliding base isolator, which ended up being very similar to Rachel's second sketch.
In my third sketch, I decided to try X cross braces with an elastomeric base isolator. And for reasons previously discussed, Emma and I decided against using X cross braces.
In my last sketch, I tried to incorporate a fluid damper base isolator, as well as using inverted V cross braces. The use of the fluid damper base isolator would provide the building with maximum flexibility, and I thought this would be helpful.
In the end, Emma and I decided to use inverted V cross braces so that we could distribute the weight evenly and elastomeric base isolators. We drew this model in our blueprint.
Rachel's first sketch became our blueprint. We like this design the best because it effectively distributes the weight of the floors onto the frame and allows the entire building to have full flexibility.
While drawing out blueprints, we had issues with making every measurement perfect.
During my experience, I made the mistake of finishing my blueprint without adding in the width of the balsa wood, which threw off all of my measurements.
During my experience, I made the mistake of incorrectly measuring the bottom floor to the first floor. I didn't take into the account that the bottom level is a different measurement than all of the other ones.
Other than those few issues, we worked efficiently and finished our blueprints in one period.
That gave us the opportunity to start building the next day, and we felt like we got a head start to make a good game plan for our building.
The second day was our trial and error day with the physical building process, as well as where we placed our iPad to record our work. My idea was to build off of the foundation and work our way up level by level. I was planning on having the columns be placed first, and then the floors would follow.
I thought that we should secure the top floor so that the outside columns were perfectly perpendicular to the ground. In order to do this, I believe that we should glue the columns to the top floor upside down and then flip it over and glue the columns to the side of the foundation.
First, we tried gluing the columns to the foundation. However, the glue wasn't drying fast enough, so they kept falling.
We then tried my idea, which ended up working. However, after the columns were glued to the top floor, we had to flip the building, which took a lot of precision.
After the building was flipped, we started working on adding our floors in during the next lab day. We had to measure the distance between each of the floors and then make it level and proceed to glue the floor plates in with precision.
After all of the floor plates were glued in, we started making our floor supports. Through trial and error, we figured out the length of the piece of balsa wood that would lay underneath each floor plate for support. We proceeded to flip the building over once again to place each piece of wood.
On the next day, we began making cross braces. We struggled a lot with these because we didn't know what angle we wanted to cut the wood at. We did a lot of trial and error, and on the next day we finally figured out that we wanted a 60-degree angle sanded down on the ends of both pieces of wood in order for them to lean on each other nicely.
After we glued in all of the cross braces for the first level, we figured out a system and finished the rest within 3 periods. On our last day of building, we constructed our elastomeric base isolator. I brought in rubber cooking pads that people use to rest hot objects on that we cut up into little squares. In between 3 squared pieces of the rubber, we placed flexible plastic that took the place of shims in the real building.
When we were constructing this, we didn't take into account that the rubber and plastic would not glue together. We tried rubber banding them together or holding them down with tape, but nothing was working. In this case, we tried to leave a rock on the rubber pieces overnight, hoping they would glue together in time for the last building day, but the glue ended up drying out and not gluing together what we wanted.
On the last building day, Emma and I experienced major difficulties. We ended up taking each rubber and plastic sandwich and wrapping it in tape. Then we glued that tape-wrapped isolator to the bottom of the foundation. Finally, after lots and lots of wrapping and tape, we had a sturdy base isolator.
Compared to our blueprint, our building was a very accurate representation of what we had in mind. Except for our floor supports, we did not change anything from our blueprint.
We believe our building is very well constructed, and other than our base isolator, everything went to plan. However, because our isolator wasn't very reliable, we don't believe that our building will last very long because the tape won't hold.
We predict that our building will last around 30 seconds because once the shaking gets very fast, we believe it'll ruin our building. Our building ended up not falling off the machine at all.
As you can see in the video, our base isolator was shaking like crazy because it was poorly constructed. However, it did stay up the whole minute and 30 seconds.
We believe our tower was super strong because we carefully measured everything multiple times, and we were very diligent and careful when we were building this. We also utilized our time wisely because we weren't rushed at the end and had time to fix our mistakes.
Our tower exceeded our expectations because we felt like it would only last for 30 seconds max, but it lasted the whole time.
Although our building stayed on the entire time on the earthquake machine, if we could do this project again, we would bring different glue. We did not read the yellow packet close enough because we thought we could not bring any other glue. If we did, our elastomeric base isolators would have glued the way we wanted and may have been more sturdy throughout the testing process. Throughout this project, Rachel and I learned how to manage our time better, as well as how to work better as a team.
We listened to each other's ideas to build a final product that we were proud of.